Hi third year and welcome to this lesson on calculations from balanced equations. This is actually week 11. And for today's lesson, the prior knowledge we need is to be able to write balanced equations. Now, firstly, if you can't do this, you should probably go back to the lesson that Mr. Shepherd did a few weeks ago and refresh your knowledge of that and practice that skill. We're actually using balanced equations today, so we need to understand that a balanced equation tells us the mole ratio of reactants to products. We also need to be able to use the mole relationship to work out quantities of substance in reactions. So the mole relationship is summarised with this triangle here. Number of moles is the mass divided by the gram formula mass, or mass is number of moles multiplied by gram formula mass. So if we pop those into that triangle there, we get the two relationships that we need. Number of moles is mass over gram formula mass, and mass is number of moles times gram formula mass. So that's what we need to be able to use for today. In today's learning, given the mass of a reactant and a balanced equation, I can calculate the mass of product in a reaction. We can actually extend this to say mass of product or other reactants in a reaction, okay? Because as long as we know the mass of one thing within the equation, we can work out masses of the other things. For these notes, remember everything that's in this coloured box, that's what we need to make sure is in our class notes. So make sure you pause the video to give yourself plenty of time to copy down all the important information. Okay, so a balanced chemical equation tells us the mole ratio of the reactants and products. So in this example, we've got 1 mole of nitrogen, which reacts with 3 moles of hydrogen and produces 2 moles of ammonia, okay? And all these moles represent masses, okay? Because if we say that the gram formula mass is the formula mass expressed in grams, then we can say, well, 1 mole of nitrogen, that actually has a mass of 28 grams, because relative atomic mass of nitrogen is 14 multiplied by 2 is 28. For the hydrogen, H is 1, and then we multiply it by 2 to get 2, and then we multiply that by 3 to get 6. So 3 moles of hydrogen is 6 grams. If we come over here and look at the ammonia, well, what is the formula mass of ammonia? NH3, I've got 14 for the nitrogen, and then 3 times 1 is 3 for the hydrogen, so that's 17. So if 1 mole is 17, then 2 moles is going to be 2 times 17, which is 34 grams. So we can see that 28 grams plus 6 grams equals 34 grams, okay? That's why our equations need to be balanced so that the masses make sense, so that we're not gaining or losing mass when we go from the reactant side to the products side. Okay, if we know the mass of a substance in a reaction, we can use the mole ratio to calculate the mass of other substances. So, for example, if we know the mass of nitrogen that's used, let's say it was 28 grams of nitrogen, we can calculate the mass of hydrogen needed. Okay, so if 28 grams reacted, we know we would need 6 grams of hydrogen, and we would get, if all of it did react, 34 grams of ammonia. Now, in reality, not all of the nitrogen and hydrogen would go towards making ammonia, and that's something that's covered later on in chemistry. But we are just doing the theoretical calculation today. So we're just saying, in theory, it could all make that. The mass of the atoms would total that, okay? We could then also say, well, let's say it was 2.8 grams. Well, that would react with 0.6 grams to form 3.4 grams, okay? So we can use the ratio to tell us information about what masses will react, as long as we know one mass. So let's start with an example. What mass of hydrogen is required to react with 70 grams of nitrogen? In all of these examples, I'm going to put this magic triangle over in the corner. So mass at the top, number of moles, and gram formula mass underneath. and I'm going to use that triangle whenever I need to work something out, okay? Now, the equations are all balanced in these examples, and we need to just make sure that we know what the mole ratio is. So in this example, I'm going to get the highlighter out. So what mass of hydrogen, so here's the hydrogen, is required to react with 70 grams of nitrogen? Okay, there's the nitrogen. So the balanced equation tells us that 1 mole of nitrogen react with 3 moles of hydrogen. How many moles am I starting with? We don't know that yet. We know that it's 70 grams, but how many moles is 70 grams? Let's work it out. Number of moles is mass divided by gram formula mass. So the mass is 70. What's the gram formula mass? Well, nitrogen's relative atomic mass is 14 times 2, because it's diatomic, is 28. So we're doing 70 divided by 28. And you can do that in your calculator. And it comes out as 2.5, and our units are going to be moles, okay, because we're working out a number of moles. Now here's the key part of this question. If 1 mole gives 3 moles, what would 2.5 moles give? Well, it would give 3 times 2.5 moles, which is 7.5 moles. But what's the mass? Well, we work out mass using number of moles multiplied by the gram formula mass. So that's going to be 7.5 multiplied by the gram formula mass of hydrogen is 2. So 7.5 times 2 is 15 grams. And that is our final answer for this question. So because we know that 1 mole would give 3 moles, then 70 grams would give 15 grams. It would react with 15 grams, sorry. Okay? That's one type of question we might get asked. Here's another one. Okay, so if 3.5 kilograms of nitrogen reacts, what mass of ammonia will form? Okay, so let's get the highlighter out and work out what the question is asking us. So if 3.5 kilograms of nitrogen, there's the nitrogen here, reacts, what mass of ammonia will form? Here's the ammonia. So we've got the mole ratio, it's 1 to 2. And to work out numbers of moles, we need to have our triangle. So mass, number of moles, and gram formula mass. Okay, so let's say how many moles of nitrogen do we have at the start? Well, we have a mass. We don't have a number of moles yet, so we need to use this triangle to help us work it out. Okay, so nitrogen, we've got number of moles is mass divided by the gram formula mass. What about 3.5 kilograms? How many grams is that? Well, 1 kilogram would be 1,000, so 3.5 kilograms would be 3,500, whoops, too many zeros, 500 grams. So 3,500 divided by, nitrogen is N2, remember, so it's 14 times 2, which is 28. So 3,500 divided by 28 is 125, and that answer is in moles. Okay, let's go back to our mole ratio then. If 1 mole gives 2 moles, then 125 moles would give 2 times 125, which is 250 moles. What is the mass of those 250 moles? Well, mass is number of moles times the gram formula mass, where N is 250 and the gram formula mass of ammonia, let's write it under here as well, it's NH3, so it's 14 plus 3 times 1 is 3, which is 17. So 250 times 17 is 4,250 grams, and that is our final answer. Okay, So that's roughly what we need to do for these equations. All we're doing is we're using the mole ratio and we're calculating number of moles or masses using this relationship. Let's look at a couple more examples just to get us a bit more familiar with this technique. Okay, so often questions are phrased like this, using the balanced equation and so on. So using the balanced equation, calculate the mass of potassium oxide, that's the potassium oxide, that is produced when 7.8 grams of potassium, here it is there, reacts with excess boron oxide. Now this word excess just means that we've got plenty of the boron oxide. We've got way more than we need. So the amount of boron oxide is not going to affect how much potassium oxide we get. It's only the potassium that's going to affect that. So let's write our mole ratio underneath. So it's 6 moles is going to give 3 moles. So that's like a 2-to-1 ratio, isn't it? So let's use our relationship, mass, number of moles, and gram formula mass. And firstly, we need to work out the number of moles of potassium we have at the start. So number of moles is mass divided by gram formula mass. So 7.8 divided by potassium's relative atomic mass, which is 39. So 7.8 divided by 39 equals 0.2 moles. Now, if 6 moles gives 3 moles, then 0.2 moles will give 0.1 moles. But what's the mass of that? Well, mass is number of moles multiplied by the gram formula mass. So that's going to be 0.1 multiplied by, let's calculate it for potassium oxide. We haven't done that. So K2O, we've got 2 times 39, which is 78, plus a 16, which is 94. So 0.1 times 94, so that's going to be 9.4 grams. And that's our final answer for this one. Okay, you'll notice in all of these examples, we're doing exactly the same method, okay? We're just using mole ratio and mole relationship every time. Here's another one. Using the balanced equation, calculate the mass of dinitrogen pentoxide. Dinitrogen pentoxide, which is over here, that is produced when 280 grams of nitrogen reacts with excess oxygen. Okay, so let's write our mole ratio underneath. It's 2 moles to 2 moles. That's a 1-to-1 ratio, so we're not going to need to do any multiplying out. And then let's write our mole relationship. So we're happy with what we need to multiply or divide to work out the unknown. So let's start then with the nitrogen, because we know most about that. We've got a mass, so we can use that mass. We can say that the number of moles is the mass divided by the gram formula mass. Hopefully you're getting the idea now. 280 divided by, and remember it's the diatomic nitrogen. Just so we're clear, it's this number here that's the reason why we're multiplying the N value, which is 14 by 2, because it's diatomic, it's N2. So that's 28. 280 divided by 28 is 10. So 10 moles, well, what about the mole relationship? It says 2 moles gives 2 moles. So 10 moles is going to give 10 moles. What's the mass of that? Mass is number of moles times the gram formula mass. So that's 10 multiplied by, let's work it out for dinitrogen pentoxide. So 5 times 16 is 80, plus 2 times 14, which is 28, so that's 108. So 10 times 108 is going to be 1,080 grams. Next example. Using the balanced equation, calculate the mass of nitrogen that would react with 5.32 grams of cesium. So mass of nitrogen, that would react with 5.32 grams of cesium. Okay, so in this one, we're looking at a ratio of reactants, okay? So according to the balanced equation, that's 6 moles of cesium that reacts with 1 mole of nitrogen. Now, what we've got the most information about is the cesium, because we've got a mass for that. So the number of moles is going to be equal to the mass divided by the gram formula mass, as it always is. The mass is 5.32. Now, I don't know the relative atomic mass for cesium off the top of my head, so let's look in our data booklet. Here is cesium right at the top of the screen. So we can see it's 133 is the relative atomic mass. 133. So 5.32 divided by 133 is 0.04 moles. Okay, so if 6 moles react with 1 mole, then 0.04 is going to react with, well, we need to divide that by 6, don't we? Which is, we need to divide it by 6. 0.04 divided by 6 is 0.007. Approximately, it's 666, but we'll just round it to one significant figure. So that will mean that the mass is equal to the number of moles times the gram formula mass. Number of moles is 0.007. Then multiply that by, remember nitrogen is N2, so that's going to be 28. So times 28 is approximately 0.19. Now, if I had I've left it in my calculator as the exact value of 0.00666666 and so on recurring. Let me just see what happens if we do 0.007 times 28. Yeah, it comes up at 0.196, so it's approximately 0.2. Okay, but this is close enough depending on which method we've actually used. That's okay, it's going to be in grams, and that is our final answer, folks. Okay, combustion equations are really common examples for calculations from balanced equations. And this one here, we've got how much carbon dioxide, so this is the carbon dioxide here, would be produced from the complete combustion of 5.5 grams. Let's just change the colour of that one. So carbon dioxide, let's put that over here, of 5.5 grams of propane. So here is the propane over here. Let's write our mole relationship. All we need to worry about is the carbon dioxide and the propane. So it's 1 mole to 3 moles. Okay. Now, we need to work out the number of moles of propane that we have at the start. So that's mass divided by gram formula mass. So 5.5 divided by, what is the formula mass for propane? Well, C3H8. So we've got 3 times 12, which is 36. And then 8 times 1, which is 8. So that's 44. So 5.5 divided by 44 is 0.125 moles. Now, the ratio is 1 to 3, so 0.125. I'm going to need to multiply that by 3 to get 0.375 moles. That's how many moles of carbon dioxide I'm going to get. What is the mass of that? Well, mass is number of moles times the gram formula mass. So 0.375 times, for carbon dioxide, we've got 12 plus 2 times 16, which is 32, which is 44. They've actually got the same gram formula mass. So we're getting an answer of 16.5 grams. That is the mass of carbon dioxide we're going to get. Okay, very last example. How much rubidium phosphide which is over here, would be produced when 1.71 grams of rubidium, over here, reacts with excess phosphorus. So our mole ratio, 3 moles to 1 mole. And again, let's look at the data booklet for rubidium. So if we find rubidium, it's at the top of the right-hand column, it's 85.5. So 3 times 85.5. No, wait. 85.5. Sorry. The number of moles is 1.71, which is our mass, divided by 85.5. 1.71 divided by 85.5 is 0.02 moles. That's how many moles we've got. Now the ratio is 3 to 1, so it's going to be 0.02, and then we divide it by 3. And then we get 0.007. It's actually the 666 again, but we can just round it for now. That's how many moles we get. What's the mass of that? Well, the mass is the number of moles times the gram formula mass. The gram formula mass of rubidium phosphide, so let's calculate that, Rb3p. So rubidium was 85.5, wasn't it? And we times that by 3. So that's 256.5. And then phosphorus is 31. So plus 31, and then we get 287.5. So 0.007 times 287.5. And we get an answer of 2.0125 grams. That's our final answer for that one. Okay. So you'll see in all of these examples, we've used exactly the same technique. We're just calculating the number of moles and then the mass, and we're using the same mole relationship and the molar statement to help us work that out. Okay, have a go at trying some of the practice examples and let us know how you get on. Thanks, everyone.